Sit back and enjoy 2 hours of fascinating facts you didn't know. Don't forget to leave a like and subscribe. Let's get started.
Tonight, we will journey to the most enigmatic corners of the universe, where every discovery uncovers new mysteries and every answer raises even deeper questions. We will explore phenomena that challenge our understanding, colossal structures that seem impossible, and secrets that science is still trying to unravel. Dark matter holds galaxies together, yet no one truly knows what it is. When astronomers calculated the speed at which galaxies rotate, they discovered something astonishing. Based on all the visible matter, the stars should have been flung out into space. Instead, they remain bound together as though an enormous amount of invisible mass were exerting gravity on them. That unknown substance was named dark matter. Although it emits no light, reflects no radiation, and has never been observed directly, scientists estimate that it makes up approximately 85% of all the matter in the universe. Its existence is inferred solely from its gravitational effects on galaxies, galaxy clusters, and the large-scale structure of the cosmos. Decades of experiments have attempted to detect it without definitive success. One of the greatest mysteries of modern astronomy is that most of the matter in the universe appears to be made of something whose true nature remains completely unknown. There is an immense region of space where there are almost no galaxies. About 700 million light-years from Earth lies a gigantic structure known as the Eridanus supervoid. It is one of the emptiest regions ever identified in the observable universe. It spans hundreds of millions of light-years and contains far fewer galaxies than various cosmological models predict. Some researchers have proposed that this void could partially explain an anomaly observed in the cosmic microwave background known as the cold spot. However, other studies suggest that the supervoid alone would not be enough to fully account for that unusual feature. Although vast voids are a natural part of the universe's large-scale structure, the exact origin and properties of this enormous region remain under investigation. In a cosmos filled with galaxies, there are also places where apparent emptiness reaches dimensions that are difficult to imagine. Black holes may be hiding information that we still do not know how to recover. According to general relativity, any object that crosses a black hole's event horizon can never return. However, quantum mechanics states that information should never be completely destroyed. This apparent contradiction gave rise to one of the most important problems in theoretical physics, the black hole information paradox. Various proposals suggest that the information could somehow be preserved in Hawking radiation, remain encoded on the event horizon, or emerge through phenomena that are still unknown. So far, no explanation has been confirmed experimentally. Solving this mystery will likely require a theory that unifies gravity with quantum mechanics, a goal that physicists have pursued for decades. Understanding what truly happens inside a black hole could transform our view of the universe. Dark energy appears to be accelerating the expansion of the universe, yet no one knows its true nature. For much of the 20th century, scientists believed that gravity would gradually slow the expansion that began with the Big Bang. However, in the late 1990s, observations of very distant supernovae revealed exactly the opposite. The universe is not only continuing to expand, but that expansion is accelerating over time. To explain this behavior, cosmologists propose the existence of an unknown form of energy called dark energy. It is estimated to account for nearly 70% of the universe's total energy content, far exceeding both ordinary matter and dark matter. Despite its enormous importance, it is still unknown whether it represents a property of empty space, a new physical field, or an entirely different phenomenon that we have yet to understand. Some galaxies appear to have existed much earlier than current models expected. Thanks to observations made with next-generation telescopes, astronomers have identified extremely massive galaxies that were already present when the universe was only a few hundred million years old. According to many models of galaxy formation, building structures that large should have required much more time. Although many of these observations are still being analyzed and refined, they have inspired new research into how quickly the first stars, black holes, and galaxies could have formed. This does not necessarily mean that the current cosmological model is incorrect, but it does suggest that there are still processes in the early universe that we probably do not fully understand. Every new telescope is revealing a primordial universe far more complex than anyone imagined just a few years ago. There is a gigantic structure in the universe, so vast that it challenges what we expected to find. On the largest scales, cosmological models predict that matter should be distributed relatively evenly. However, astronomers have identified enormous groupings of galaxies stretching across billions of light-years. Among them is the Hercules Corona Borealis Great Wall, an immense concentration of galaxies identified through the study of gamma-ray bursts. If its estimated size is fully confirmed, it would be one of the largest structures ever observed. Some researchers debate whether it truly forms a single structure or whether it is actually several separate groupings aligned from our perspective. Regardless of the final answer, its enormous size continues to raise questions about how such an extensive region could have formed within the time available since the universe began. Supermassive black holes appeared far too early in the history of the universe. At the centers of many galaxies are black holes with masses equivalent to billions of suns. What is astonishing is that some of them already existed when the universe was less than 1 billion years old. According to many current models, forming such gigantic objects through the gradual accumulation of matter should have taken much longer. To explain this mystery, researchers have proposed several hypotheses, including the direct collapse of enormous gas clouds, episodes of extremely rapid growth, or the existence of much more massive initial seeds than previously believed. So far, none of these explanations has been fully confirmed. Understanding how they grew so quickly remains one of the greatest unanswered questions in modern astrophysics. The observable universe may be only a tiny part of a vastly larger cosmos. Because light travels at a finite speed and the universe has a finite age, we can observe only the region whose light has had enough time to reach us since the Big Bang. This immense sphere is known as the observable universe. However, there is no evidence that the universe ends exactly at that boundary. Beyond it, there could be a region vastly larger, perhaps even infinite, that we will never be able to observe directly because its light will never reach Earth. This means that everything we know may represent only a tiny fraction of a much greater reality. One of the greatest mysteries of cosmology is determining whether the universe has a true boundary or whether it extends far beyond everything we will ever be able to see. The oldest radiation in the universe contains subtle anomalies that continue to spark debate. The cosmic microwave background is the lingering glow of the Big Bang and represents the oldest light we can observe. Although it is remarkably uniform, it contains tiny temperature variations that made the formation of galaxies and galaxy clusters possible. However, in addition to those expected fluctuations, scientists have found several anomalies whose interpretation remains under debate. Among them are the so-called cold spot and an apparent alignment of certain regions of the sky informally known as the axis of evil. Some researchers believe these features may simply be the result of statistical chance, while others are investigating explanations involving cosmic structures or physical processes that are still unknown. So far, there is no definitive consensus on the origin of these intriguing irregularities. No one knows for certain what happened during the universe's very first instant. Current theories describe the evolution of the cosmos with remarkable precision, starting from an extremely tiny fraction of a second after the Big Bang. However, when we trace time back even further, the equations no longer provide reliable answers. Under those extreme conditions, where gravity and quantum mechanics should operate simultaneously, the known theories are no longer sufficient. Various models propose scenarios such as a cosmic bounce, eternal inflation, or even a universe born from an earlier one, but none has been proven through observations. That initial instant remains one of the greatest mysteries in all of physics. Understanding what happened at that moment could reveal why space, time, and the fundamental laws that govern the universe exist. Apparently, empty space may not actually be empty. Even in the regions with the least amount of matter, quantum mechanics predicts that the vacuum is filled with tiny fluctuations in which pairs of particles constantly appear and disappear over extraordinarily brief intervals. These processes, known as quantum vacuum fluctuations, have been indirectly confirmed through various observable physical effects. Some cosmologists even propose that the tiny irregularities generated by these fluctuations during the earliest moments of the universe later became the seeds from which entire galaxies and galaxy clusters formed. It is astonishing to think that the largest structures in the cosmos may have originated from quantum phenomena occurring on scales vastly smaller than a single atom. Dark worlds may exist, wandering between the stars without belonging to any solar system. These worlds, known as rogue planets, were most likely ejected from their planetary systems during gravitational encounters with other planets or stars. Since then, they have traveled through the galaxy in complete darkness, receiving no constant light from a sun. Some may retain enough internal heat to sustain liquid oceans beneath thick layers of ice for billions of years. Others would be completely frozen worlds silently drifting through interstellar space. Because they reflect very little light, they are extremely difficult to detect, leading scientists to believe that there may be far more of them than we currently know. Our galaxy could be filled with invisible worlds traveling alone among the stars. Most energetic explosions in the universe still conceal part of their origin. Gamma-ray bursts release more energy in just a few seconds than the sun will emit over its entire lifetime. Many occur when extremely massive stars collapse into black holes, while others appear to originate from the merger of neutron stars. However, there are still events whose characteristics do not fit completely into either of these scenarios. Some display unexpected durations, unusual energy outputs, or properties that challenge traditional classifications. Every new observation provides valuable information, but it also reveals new questions. These incredibly brief flashes are among the most violent phenomena ever observed and continue to be one of the most active areas of research in modern astronomy. Neutron stars contain matter in a state that cannot be reproduced on Earth. When a very massive star exhausts its fuel, it can collapse into an object where more than the Sun's mass is compressed into a sphere only about 12 miles across. Inside, the pressure reaches such extreme levels that scientists still do not know exactly how matter behaves. Various possibilities have been proposed, including exotic particles, quantum condensates, and even matter made of free quarks. None of these hypotheses has been definitively confirmed. Neutron stars serve as true natural laboratories, where physics explores conditions that cannot be recreated by any known experiment on Earth. Most of the universe may never be directly observable. As the universe continues expanding at an accelerating rate, extremely distant galaxies move farther away ever more quickly. A time will come when many of them will be so distant that their light will never reach us again. For astronomers in the far future, the visible universe will be much smaller than it is today. Countless galaxies will disappear forever beyond the observable horizon, not because they cease to exist, but because space itself will continue expanding between them and us. Paradoxically, the more time passes, the smaller the portion of the universe that can be studied directly, making the cosmos an increasingly mysterious place. Some galaxies appear to contain almost no dark matter, although no one knows why. For decades, astronomers believed that virtually all galaxies required large amounts of dark matter to remain gravitationally bound. However, some recent observations have identified galaxies whose stars appear to move as though there is very little dark matter within them. Among the best-studied examples are the galaxies DF2 and DF4, whose true nature remains the subject of intense debate. Some researchers believe they are genuinely deficient in dark matter, while others suggest that the distance or mass measurements may require revision. If these objects truly are what they appear to be, they would force scientists to rethink part of what we know about galaxy formation. Discovering why some galaxies seem to require very little dark matter while most depend heavily on it remains one of the most intriguing mysteries in modern astronomy. The universe may contain extra spatial dimensions that we will never be able to perceive directly. Our everyday experience reveals 3 spatial dimensions and 1 dimension of time. However, some physical theories, such as certain versions of string theory, propose the existence of additional dimensions that are extraordinarily small and curled up within themselves. These dimensions would be so tiny that no experiment conducted so far has been able to observe them directly. Although these ideas remain hypothetical and still lack experimental confirmation, they offer possible explanations for some of the fundamental properties of particles and the forces of nature. If their existence were ever proven, it would mean that reality has a far more complex structure than our senses can perceive. Much of the universe may remain hidden simply because we evolved to observe only a small part of it. No one knows whether our universe is the only one that exists. Various cosmological hypotheses suggest that the observable universe could be part of a much larger reality composed of multiple universes, known as the multiverse. Depending on the model, each universe could have different physical constants, different fundamental laws, or even an entirely different history. Some versions of the concept arise from eternal cosmic inflation, while others emerge from certain interpretations of quantum mechanics. However, there is currently no observational evidence confirming the existence of other universes. The idea remains a widely discussed theoretical possibility, but it has not been proven. If it were ever verified, it would radically change our understanding of the place the known universe occupies within a much greater reality. Galaxies rotate as though they are following a rule that we still do not fully understand. By measuring the rotation speeds of thousands of galaxies, astronomers discovered an astonishingly precise relationship between the amount of visible matter and the speed at which their stars orbit. This connection is much tighter than many models predicted and has sparked intense debate about its origin. Some scientists believe it reflects the influence of dark matter during galaxy formation, while others suggest it could indicate that our understanding of gravity needs to be modified under certain conditions. No explanation has yet convinced the entire scientific community. The fact that very different galaxies appear to follow the same rule remains one of the greatest mysteries in modern cosmology. We still do not know exactly what happens at the center of a black hole. General relativity predicts that after crossing the event horizon, all matter would ultimately become concentrated in a region known as a singularity, where density would become infinite and the equations would no longer have physical meaning. However, most physicists believe this description reflects the limits of the theory rather than the actual existence of an infinite singularity. It is thought that a future theory of quantum gravity will accurately describe what happens under these extreme conditions. Until such a theory exists, the true interior of a black hole will remain hidden both by the laws of physics and by the impossibility of making direct observations. It is one of the few places in the universe where our best theories no longer provide complete answers. The ultimate fate of the universe remains unknown. Current observations indicate that the universe's expansion continues to accelerate because of dark energy. If this behavior remains unchanged for trillions of years, the cosmos would eventually evolve into an extremely cold and diffuse state known as heat death, where almost no active stars or significant sources of energy would remain. However, if the nature of dark energy turns out to be different from what we currently believe, entirely different scenarios could unfold, such as an expansion so extreme that it tears apart galaxies, stars, and even atoms, or a future slowdown followed by a possible contraction. For now, measurements favor the scenario of continued expansion, but because the true nature of dark energy remains unknown, the universe's ultimate destiny is still an open question. There are stars traveling so fast that they can escape the galaxy entirely. These hypervelocity stars reach speeds of more than 600,000 miles per hour, fast enough to overcome the gravity of the Milky Way. Many likely gained that tremendous speed after gravitational encounters with the supermassive black hole at the center of the galaxy, while others may have been accelerated by supernova explosions within binary star systems. Once ejected, they continue traveling alone through intergalactic space for millions of years. Although several of these stars have already been discovered, astronomers are still investigating how many truly exist and all the mechanisms capable of launching them at such extraordinary speeds. They are genuine cosmic travelers destined to leave forever the galaxy where they were born. First stars in the universe have never been observed directly. Shortly after the Big Bang, only hydrogen, helium, and small amounts of lithium existed. From those elements, the first generation of stars, known as population 3 stars, was formed. They are believed to have been far more massive and luminous than most stars today, and were responsible for creating many of the heavy chemical elements now found in galaxies, planets, and even our own bodies. However, none has yet been definitively identified. Because they lived for only a short time and existed more than 13 billion years ago, finding them remains one of the greatest challenges in observational astronomy. Their discovery would allow us to directly witness the beginning of stellar evolution in the universe. Tiny black holes may have formed during the universe's earliest moments. In addition to the black holes created by massive stars, some models propose the existence of primordial black holes that formed just fractions of a second after the Big Bang due to extreme density fluctuations. Depending on their mass, some would have disappeared long ago through Hawking radiation, while others may still exist today. It has even been suggested that part of dark matter could be made up of these objects, although there is currently no conclusive evidence supporting that idea. Detecting them would open a unique window into the earliest moments of cosmic history and provide fundamental clues about the birth of the universe. Every new observation of the universe seems to answer some questions while creating many more. Over the past few decades, space and ground-based telescopes have allowed astronomers to discover thousands of exoplanets, measure the cosmic microwave background with extraordinary precision, capture images of black holes, and detect gravitational waves produced by collisions between extremely massive objects. However, each of these breakthroughs has also revealed unexpected phenomena that challenge current theories. Dark matter remains invisible. Dark energy is still unexplained. The origin of the Big Bang remains unknown, and numerous objects display behaviors that are difficult to interpret. The deeper we look into the cosmos, the more apparent it becomes that we have only begun to understand a tiny fraction of everything that exists. The greatest mystery of the universe may be just how much we still have left to discover. The universe emits a faint gravitational hum that stretches across the galaxy. For decades, scientists sought to detect a permanent background of gravitational waves produced by countless pairs of supermassive black holes orbiting one another in very distant galaxies. Instead of searching for a single powerful signal, they used a network of pulsars, neutron stars that emit radio pulses with extraordinary regularity. If a gravitational wave passes through the space between Earth and a pulsar, it slightly alters the timing of those pulses as they reach our radio telescopes. After years of observations, several international collaborations found consistent evidence of this gravitational wave background. Although much remains to be understood about its exact origin, the discovery opened an entirely new way to study the universe. For the first time, astronomers began listening to the collective murmur produced by some of the most massive objects in the cosmos. Some stars appear to disappear without producing a visible explosion. Normally, when a very massive star exhausts its fuel, it explodes as an extremely bright supernova. However, various observations suggest that some may collapse directly into a black hole without generating a spectacular explosion. In these cases, the star would simply fade until it almost completely vanished from the sky. Astronomers have identified several candidates that may correspond to this phenomenon, although they continue to investigate each case to rule out other explanations. If these silent disappearances truly occur, it would mean that some black holes in the universe are born in a much quieter way than previously believed. Even the deaths of some of the largest stars may take place with almost no visible trace. The Hubble constant still does not have a definitive value. One of the most important goals in cosmology is to measure the rate at which the universe is expanding with the greatest possible precision. However, the two most accurate methods currently available produce results that do not fully agree with one another. Measurements based on the cosmic microwave background indicate a slightly different expansion rate than those obtained from observations of nearby variable stars and supernovae. This discrepancy, known as the Hubble tension, has persisted despite numerous improvements in both observations and the models used. Some scientists believe it may be caused by systematic errors that have not yet been identified, while others think it could point to new physics beyond the current cosmological model. Resolving this difference is one of the highest priorities in modern astronomy. Galaxies may be surrounded by enormous oceans of gas that we are only beginning to study. Beyond the bright regions where stars are concentrated, many galaxies are enveloped by gigantic halos of extremely diffuse gas that can extend hundreds of thousands of light-years. Although this material is very difficult to observe directly, it contains a substantial amount of matter and plays a fundamental role in the birth of new stars. Some of this gas slowly falls into the galaxy, fueling future episodes of star formation, while another portion is expelled by supernova explosions and the activity of supermassive black holes. Understanding how this immense gaseous reservoir circulates is essential for explaining the evolution of galaxies. However, because of its extremely low density, it remains one of the most difficult regions of the universe to study. Neutrinos constantly pass through your body without you ever noticing. Every second, trillions of these tiny particles pass through Earth and travel through people, buildings, and even the entire planet while interacting with matter only on the rarest occasions. They are produced by the sun, supernova explosions, cosmic rays, and numerous nuclear processes occurring throughout the universe. Their ability to pass through enormous amounts of matter makes them exceptional messengers of extremely energetic phenomena. However, that same property also makes them extraordinarily difficult to detect. Neutrino observatories use enormous reservoirs of ultra-pure water or ice located deep underground or beneath the Antarctic ice to record only a handful of interactions. Even though they pass through us constantly, neutrinos remain some of the most mysterious particles known to science. Stars partially made of dark matter may have existed. Some theoretical models propose that during the universe's first few million years, certain regions with enormous concentrations of dark matter may have given rise to objects known as dark stars. Unlike ordinary stars, whose energy comes primarily from nuclear fusion, these objects would have generated part of their energy through the annihilation of dark matter particles within their interiors. If they truly existed, they could have grown to colossal sizes before collapsing into extremely massive black holes. So far, there is no observational evidence confirming their existence, but they remain an intriguing possibility for explaining some of the supermassive black holes observed in the early universe. It is a fascinating idea that remains completely open to future research. Most galaxies in the universe can never be visited, even if we could travel at the speed of light. Because space is expanding at an accelerating rate, countless galaxies are moving away from us so rapidly that the distance between them and us continues to grow even as their light travels toward our location. Although no nearby galaxy is moving locally faster than the speed of light, the expansion of space itself causes many distant regions to remain forever beyond our reach. This means that even if a spacecraft could travel exactly at the speed of light, it would never be able to reach much of the observable universe. Cosmic expansion places fundamental limits on which regions of the universe will ever be able to influence one another in the future. Countless galaxies will remain forever beyond the reach of any civilization. Magnetars possess the most powerful magnetic fields known in the universe. These extremely rare neutron stars pack a mass comparable to that of the Sun into a sphere only about 12 miles across, but their most extraordinary feature is their immense magnetic field. At their surface, it can be trillions of times stronger than Earth's magnetic field. Occasionally, they release enormous amounts of energy through violent rearrangements of that magnetic field, producing some of the most powerful bursts ever recorded within our galaxy. Scientists are still investigating exactly how these objects form and why only a small fraction of neutron stars evolve into magnetars. Understanding them will help explore physics under conditions that cannot be reproduced in any laboratory on Earth. We still do not know with certainty how the universe's so-called dark ages came to an end. After the Big Bang, there was a period when no stars yet existed to illuminate the cosmos. The universe was filled primarily with neutral hydrogen and remained almost completely dark. With the birth of the first stars and galaxies, a process known as reionization began, during which intense radiation transformed that hydrogen once again. However, scientists still debate exactly which objects were primarily responsible for driving this change. Some studies point to the earliest small galaxies, while others suggest that active black holes or additional sources of radiation may also have played a role. Reconstructing this chapter remains one of the greatest challenges in observational astronomy because it took place more than 13 billion years ago. Every answer we obtain about the universe seems to reveal an even deeper question. Humanity has discovered that we live in one galaxy among hundreds of billions, that space continues to expand, and that black holes, gravitational waves, and planets orbiting other stars exist. However, we still do not know what dark matter is made of, the true nature of dark energy, exactly how the universe began, what happens inside a black hole, or whether other forms of life exist in the cosmos. Each generation builds more powerful telescopes and develops more precise theories, yet the horizon of knowledge continues to move farther away. Perhaps the greatest mystery is not a specific object in the universe, but the immense number of questions that still remain unanswered. The vacuum of space may possess its own energy that dominates the universe. At first glance, empty space appears to contain absolutely nothing. However, modern physics indicates that even the vacuum has quantum properties and may store a small amount of energy distributed throughout the cosmos. If that energy truly corresponds to the so-called cosmological constant proposed by Albert Einstein more than a century ago, then it would be precisely what causes the accelerated expansion of the universe. What is surprising is that theoretical calculations in quantum mechanics predict an amount of vacuum energy vastly greater than what is observed. The difference between the two figures is so enormous that it represents one of the greatest disagreements between theory and observation in the entire history of physics. Understanding why the vacuum has exactly the amount of energy we measure remains one of the deepest mysteries of the universe. Some galaxies appear to have stopped forming stars much earlier than expected. Galaxies normally produce new stars for billions of years by using enormous reserves of interstellar gas. However, astronomers have found very massive galaxies that had almost completely stopped producing stars when the universe was still relatively young. What is puzzling is that scientists still do not fully understand which process managed to halt star formation so quickly. Some hypotheses point to the activity of supermassive black holes that expelled the gas needed to form new stars, while others propose gravitational interactions or intense bursts of star formation that exhausted the available fuel. Every new discovery forces scientists to revise models of galactic evolution and demonstrates that galaxies can follow very different paths throughout their histories. We still do not know whether space is truly continuous or has a fundamental structure. Our everyday experience leads us to believe that space can be divided indefinitely into increasingly smaller portions. However, some theories of quantum gravity propose that there may be a minimum scale known as the Planck length, below which the traditional concept of distance would no longer have meaning. At that extraordinarily tiny level, space might behave like a granular structure or experience extremely intense quantum fluctuations. So far, no observation has allowed scientists to directly test this possibility because it occurs at scales far smaller than anything accessible through current experiments. Discovering whether space is continuous or possesses a fundamental structure would profoundly transform our understanding of reality. Most of the atoms that make up your body were born inside stars that disappeared billions of years ago. Shortly after the Big Bang, only significant amounts of hydrogen and helium existed, along with small traces of lithium. Elements such as carbon, oxygen, calcium, iron, and phosphorus were created much later inside successive generations of stars through nuclear fusion. When those stars exhausted their fuel, many exploded as supernovae or expelled their outer layers, scattering those elements through space. Over millions of years, that material enriched new clouds of gas that eventually formed other stars, planets, and ultimately Earth. Every heavy atom found in living organisms is direct evidence of ancient processes that occurred inside stars that ceased to exist long before the birth of the solar system. Black holes may merge thousands of times every day throughout the observable universe without us ever seeing them directly. Since gravitational waves were first detected, observatories have confirmed numerous collisions between black holes located billions of light-years away. However, the recorded events represent only a tiny fraction of all those that probably occur across the universe. Astrophysical models indicate that these mergers may happen continuously in countless galaxies, producing gravitational waves that travel through space for millions or even billions of years before reaching Earth. The vast majority will never be detected because of their enormous distance or the current limitations of our instruments. The universe may be constantly vibrating as a result of gigantic collisions that pass completely unnoticed by us. There may be a limit to what any civilization will ever be able to learn about the universe. Even if technology continues advancing for millions of years, some regions of the cosmos will remain forever beyond our reach because of the accelerated expansion of space. In addition, some phenomena are hidden behind event horizons. Certain processes occurred before the universe became transparent to light, and some physical scales may be impossible to explore directly with current methods. This means that certain mysteries may not result solely from a lack of technology, but from fundamental limits imposed by the laws of the universe themselves. Science continues to expand human knowledge, but it also reveals that some questions may never be answered through direct observation. Some of the brightest explosions in the universe last less than the blink of an eye. Certain gamma-ray bursts last only a few thousandths of a second. During that incredibly brief interval, they release enormous amounts of energy before disappearing forever. Although many of these events are associated with the merger of neutron stars or the collapse of massive stars, some extremely short explosions remain under investigation. Detecting them is an enormous challenge because they appear completely without warning and vanish before most telescopes can point toward them. Each of these flashes provides unique information about some of the most extreme physical processes known. The Milky Way and the Andromeda Galaxy are already moving slowly toward an inevitable collision. The two galaxies are currently approaching each other at a speed of several 100,000 miles per hour and are expected to begin interacting in approximately 4.5 billion years. Although the word collision suggests a violent impact, the enormous distances between stars make it extremely unlikely that any two of them will collide directly. What will actually occur is a gigantic gravitational dance that will distort both galaxies for billions of years before creating a new and much larger galaxy. Although this event will happen in the extremely distant future, it is one of the few major cosmological events whose development can be predicted with considerable confidence using current laws of gravity. We still do not know whether the laws of physics are exactly the same throughout the entire universe. Observations made so far indicate that the same fundamental laws appear to describe both our solar system and galaxies located billions of light-years away. However, some researchers continue searching for extremely small possible variations in fundamental constants, such as the fine structure constant or the relative mass of certain particles. So far, there is no solid evidence confirming any real differences, but even a tiny variation would have enormous consequences for our understanding of the cosmos. It would mean that the rules governing the universe may not be completely uniform, forcing scientists to reconsider some of the most basic principles of modern physics. Perhaps the greatest mystery of the universe is why something exists instead of absolutely nothing. Every physical theory describes with extraordinary precision how the universe evolved from its earliest known moments, how stars are born, how galaxies form, and how fundamental particles interact. However, none provides a definitive explanation for why the universe exists in the first place. Why do the laws of physics exist? Why are there space, time, matter, and energy instead of absolute emptiness? These questions extend beyond many of the current boundaries of cosmology and the philosophy of science. After centuries of discoveries, the ultimate origin of existence remains one of the deepest mysteries humanity has ever attempted to understand. The universe may be slightly curved, but we still do not know for certain. When we think about space, we usually imagine a completely flat and infinite setting. However, the theory of general relativity allows the universe to have a slightly curved geometry. Depending on the total amount of matter and energy, space could be perfectly flat, have positive curvature similar to the surface of a sphere, or have negative curvature resembling a saddle. The most precise observations made so far indicate that the universe is extraordinarily close to being flat, but they have not completely ruled out an extremely small curvature. If such curvature were ever detected, it would change our understanding of the universe's total size and its large-scale evolution. Even the shape of space itself remains an open mystery in cosmology. Some galaxies appear to release enormous amounts of matter into intergalactic space. At the centers of many galaxies are supermassive black holes capable of releasing immense amounts of energy as they absorb gas and dust. In some cases, this activity generates gigantic jets of particles and powerful winds that expel part of the galactic material into the surrounding space. These outflows can extend for hundreds of thousands of light-years and profoundly alter the evolution of the entire galaxy by reducing the amount of gas available to form new stars. Astronomers are still investigating exactly how much influence these processes have on the growth of galaxies. A single black hole can ultimately regulate the fate of billions of stars located at enormous distances from the galactic center. We still do not know what the first light to illuminate the universe was. After the Big Bang, the universe remained without stars for millions of years. Later, the first objects capable of emitting light appeared, bringing an end to the so-called cosmic dark ages. However, scientists are still investigating exactly what first illuminated the cosmos. Some hypotheses point to the first giant stars, while others suggest that small primordial galaxies or young black holes may have played an important role. Directly observing that moment represents one of the greatest challenges in modern astronomy because of the enormous distance and age of those events. Every new telescope brings us a little closer to the moment when the universe transitioned from darkness to light. Gravitational waves may reveal objects that we will never be able to observe through light. Many phenomena in the universe emit very little electromagnetic radiation or remain completely hidden behind enormous amounts of gas and dust. However, when extremely massive objects accelerate violently, they distort space-time itself, generating gravitational waves that can travel almost entirely unobstructed for billions of years. Thanks to them, scientists have already detected black hole mergers that were impossible to observe with traditional telescopes. In the future, far more sensitive observatories may discover completely unknown phenomena, including possible collisions between primordial black holes, exotic stars, or processes that occurred during the universe's earliest moments. Gravitational wave astronomy has only just begun and may reveal a part of the cosmos that has remained completely invisible until now. There is an enormous filament of galaxies connecting regions separated by hundreds of millions of light years. The universe does not distribute galaxies randomly. Instead, they form an immense cosmic web made up of filaments, clusters, and enormous voids. Some of these filaments stretch for hundreds of millions of light years and contain thousands of galaxies bound together by gravity. Large amounts of hot gas and dark matter flow through them, slowly fueling the growth of new galaxies. Although this structure only began to be revealed a few decades ago through large-scale surveys of the sky, scientists are still investigating how it evolved in such detail from the tiny fluctuations present shortly after the Big Bang. Most of the matter in the universe appears to be arranged in a gigantic cosmic web. We still do not know whether time truly had a beginning. According to the standard cosmological model, space and time emerged together with the Big Bang approximately 13.8 billion years ago. However, when the equations are traced back to that instant, they stop describing reality correctly. Some theories propose that time began exactly there, while others suggest the existence of an earlier phase, a previous universe, or even infinite cycles of expansion and contraction. So far, none of these possibilities has been confirmed through observations. The question of what happened before the Big Bang may have no answer within our current theories, or it may require an entirely new understanding of the nature of time. There are regions of the universe whose light will never reach us, even if we wait forever. Because of the accelerated expansion of space, some galaxies are so far away that the distance between them and Earth increases faster than light can overcome. As a result, any light they emit after a certain point will never be able to reach us. Those regions will continue to exist, but they will remain completely disconnected from the observable universe forever. This boundary is known as the cosmological event horizon and represents a limit imposed not by technology, but by the expansion of space itself. Countless events are taking place at this very moment that will never be observable from Earth. Some of the most energetic particles in the universe reach Earth with energy levels that are difficult to explain. On very rare occasions, detectors record cosmic rays with energies millions of times greater than those reached by particles accelerated in the world's most powerful laboratories. Although many cosmic rays are believed to come from stellar explosions, active galactic nuclei, or other extreme phenomena, the exact origin of the most energetic events remains uncertain. These particles travel enormous distances before striking Earth's atmosphere, where they produce vast showers of secondary particles. Discovering which natural mechanisms are capable of accelerating them remains one of the greatest challenges in high-energy astrophysics. First galaxies may have been very different from those we observe today. The deepest images captured by space telescopes show extremely distant objects whose structures are far more irregular than those of many modern galaxies. Instead of displaying elegant spiral arms or clearly defined elliptical shapes, many primordial galaxies appear to be made up of small fragments that constantly interact and merge. Astronomers are still investigating how those chaotic structures evolved into the stable galaxies that now dominate the nearby universe. Directly observing this transformation will help us better understand how complex systems such as the Milky Way emerged. Every time we look at the sky, we are seeing different periods of the universe's history at the same time. Light takes time to travel through space. When we observe the moon, we see it as it was a little more than 1 second ago. Sunlight shows us the sun as it was approximately 8 minutes ago. Nearby stars appear as they were years in the past, while many distant galaxies are seen as they existed billions of years ago. The farther a telescope looks, the deeper it travels into the past. Modern observatories function as true time machines, capable of reconstructing the evolution of the cosmos by simultaneously observing objects from completely different eras in the history of the universe. The universe may contain more types of matter than we currently know. The standard model of physics describes the fundamental particles observed in experiments, such as electrons, quarks, and neutrinos, with extraordinary precision. However, these particles represent only a small fraction of the universe's total content. Dark matter, which makes up a much larger portion, has still not been directly identified. To explain it, scientists have proposed new hypothetical particles such as weakly interacting massive particles, axions, and sterile neutrinos, among many other possibilities. Large underground detectors, particle accelerators, and space telescopes continue searching for them without definitive success. The universe may be composed of an entire family of completely unknown particles that barely interact with ordinary matter and remain invisible to our current instruments. Giant galaxies continue growing even billions of years after they first formed. For a long time, scientists believed that galaxies quickly reached their final size. However, modern observations show that many massive galaxies continue to increase slowly in size by absorbing smaller galaxies that pass nearby. These mergers can last for hundreds of millions of years and profoundly alter the structure of both systems. In some cases, the stars from the smaller galaxy eventually become scattered around the larger one, forming enormous stellar halos that preserve traces of ancient collisions. Using this evidence, astronomers have reconstructed part of the history of numerous galaxies, discovering that many of them grew through a long succession of gravitational encounters that continues today. We still do not know exactly what happens when two black holes begin to merge. Gravitational waves allow scientists to detect the final moments of these collisions with extraordinary precision, but many details of the process remain under investigation. As the two black holes approach each other, they intensely distort space-time and orbit ever faster around a shared center. Eventually, they merge into a single black hole whose mass is slightly lower than the combined mass of the original two, because some of the energy is released as gravitational waves. Although computer simulations describe this process with remarkable accuracy, scientists are still studying phenomena such as the orientation of their spins, possible recoil of the resulting black hole, and the influence of magnetic fields or surrounding matter. Every new detection provides valuable information about one of the most extreme processes in the universe. The universe could be filled with planets completely covered by oceans. In addition to rocky planets and gas giants, some models indicate that worlds may exist where nearly the entire surface is covered by liquid water reaching depths of hundreds of miles. On these so-called ocean worlds, there would be no continents like those on Earth, but instead immense global seas separated from the rocky core by layers of ice formed under enormous internal pressures. Although one of these planets has not yet been confirmed with complete certainty, several discovered exoplanets have characteristics consistent with this possibility. If they are truly common, they would greatly expand the diversity of environments that exist in the universe and raise new questions about the conditions necessary for life to emerge. Supernova explosions could influence the formation of new generations of stars. When a massive star explodes at the end of its life, it releases enormous amounts of energy and expels into space the heavy chemical elements produced within it. The shock wave generated by the explosion can compress nearby clouds of gas and dust, encouraging the gravitational collapse that gives rise to new stars. In this way, the death of one star can indirectly contribute to the birth of many others. However, the same process can also disperse the available material and temporarily prevent star formation in certain regions. Understanding the balance between these effects remains an important area of research for explaining how galaxies evolve over billions of years. Some moons could contain oceans larger than all of Earth's oceans combined. Several icy moons in the solar system conceal enormous amounts of liquid water beneath thick layers of ice. Among them are Europa, Enceladus, and Ganymede, where observations indicate the existence of underground oceans kept liquid by internal heating caused by the gravitational forces of their giant planets. In some cases, those oceans could contain more water than all of Earth's seas combined. Although they remain hidden beneath miles of ice, they represent some of the most promising places to search for possible forms of life beyond Earth. Future space missions will attempt to study these fascinating frozen worlds in greater detail. Light can take millions of years to escape from the interior of a star. When we imagine light being produced in the sun's core, it is easy to think that it quickly reaches the surface. However, the reality is very different. The photons generated during nuclear fusion reactions constantly collide with atoms and particles in the solar plasma, changing direction millions of times along a completely random path. As a result, a photon may need hundreds of thousands of years, or even longer depending on the model being considered, to finally reach the sun's surface. Once there, it only takes approximately 8 minutes to travel the remaining distance to Earth. Most of its journey takes place slowly inside the star itself. Galaxy clusters contain some of the largest gravitationally bound objects in the universe. A galaxy cluster can bring together hundreds or even thousands of galaxies orbiting a common center for billions of years. In addition to the visible galaxies, they contain enormous amounts of extremely hot gas that emits X-rays and an even greater proportion of dark matter, whose gravity holds the entire system together. These gigantic concentrations serve as natural laboratories for studying the evolution of the universe on the largest scales. By analyzing their distribution, composition, and movement, cosmologists obtain essential information about cosmic expansion and the total amount of matter in the universe. Forms of life based on processes very different from those on Earth could exist. All known life uses liquid water, carbon, and a common set of fundamental molecules. However, some scientists are investigating the possibility that organisms adapted to completely different conditions may exist elsewhere in the universe. Hypotheses have been proposed about forms of life capable of developing in extremely cold environments, beneath hidden oceans, or by using different chemical compositions, although none of these possibilities has yet been confirmed through observations. Astrobiology continues to explore the true limits of life and whether the conditions found on our planet represent an exception or only one of many possibilities that could exist throughout the cosmos. Every major discovery about the universe has shown that reality is often far more surprising than we imagined. For centuries, humanity believed that Earth occupied the center of the cosmos, that the Milky Way contained every star in existence, and that the universe remained unchanged. Over time, we discovered distant galaxies, the expansion of space, black holes, exoplanets, gravitational waves, and an immense number of phenomena that once seemed impossible. The history of astronomy shows that every generation has had to abandon old certainties in order to accept a much more complex reality. Perhaps the greatest discoveries of the future will be precisely those that we are still unable to imagine today. Gravity may not behave in exactly the same way across every scale of the universe. The theory of general relativity has passed countless experimental tests and describes the movement of planets, stars, and galaxies with extraordinary precision. However, when astronomers study the universe on its largest scales, they still need to rely on dark matter and dark energy to explain many observations. This has led some physicists to wonder whether gravity might behave slightly differently across cosmological distances. Various modified theories attempt to reproduce the observations without the need to introduce certain invisible components, although none has managed to explain all the available data better than the current cosmological model. Understanding whether gravity truly changes with distance or whether we simply still do not know much of what the universe contains remains one of the most important questions in modern physics. There are gigantic clouds of gas so cold that they emit almost no visible light. Between galaxies and stars are enormous regions composed mainly of hydrogen and other light elements, where temperatures can fall to only a few dozen degrees above absolute zero. Because they emit very little light, they remained hidden for much of the history of astronomy. However, by using radio telescopes and observations at other wavelengths, scientists have discovered that these immense clouds contain the material from which future generations of stars will be born. Some have masses equivalent to millions of suns and can remain relatively stable for millions of years before beginning to collapse under the force of gravity. Much of the future of the stellar universe is already stored silently within these gigantic reservoirs of gas. We still do not know why some galaxies stopped growing while others continue forming stars actively. When we observe the universe today, we find blue galaxies filled with young stars and reddish galaxies where almost no new stars are being born. Understanding what causes this difference remains one of the greatest challenges in astronomy. In some cases, the activity of the central black hole appears to expel the gas needed for star formation. In others, gravitational interactions with neighboring galaxies or the environment within large clusters may play an important role. However, no single mechanism explains every observed case. Each new galaxy studied provides additional information about a process that is still far from being completely understood. Black holes could distort time in ways that are difficult to imagine. General relativity states that gravity curves not only space, but also time. Near a black hole, this effect reaches extraordinary levels. To a distant observer, a clock located very close to the event horizon would appear to move increasingly slowly. In theory, if it could be observed indefinitely, it would seem to stop almost completely just before crossing the horizon. However, for someone falling toward the black hole, time would continue passing normally from their own perspective. This difference between the two observers is one of the most surprising consequences of relativity and demonstrates that the passage of time depends on the gravitational environment in which each observer is located. The universe contains enormous regions that are almost completely empty and contain very few galaxies. In addition to large galaxy clusters and filaments, astronomers have identified gigantic cosmic voids that can extend for hundreds of millions of light years. In these regions, the density of galaxies is far lower than the average across the universe. Although they appear to be immense unoccupied spaces, even they contain dark matter, extremely diffuse gas, and a few isolated galaxies. Scientists study these voids because they offer ideal conditions for testing theories about the expansion of the universe and the nature of gravity. Paradoxically, some of the most interesting places for understanding the cosmos are precisely those where almost nothing appears to exist. Exoplanets with skies completely unlike any landscape on Earth may exist. Thanks to the discovery of thousands of planets orbiting other stars, astronomers have confirmed that planetary systems display enormous diversity. Some planets orbit two suns at the same time, others are so close to their star that a year lasts only a few Earth hours, while some gas giants have temperatures high enough to vaporize metals. Depending on their atmospheres, an observer standing on their surfaces might see skies with colors very different from Earth's blue sky, multiple sunrises, or stars occupying a large part of the horizon. Although we still cannot directly photograph these landscapes in great detail, atmospheric models allow us to imagine worlds whose appearance would be completely different from anything known in the solar system. The largest stars live much shorter lives than smaller ones. It might seem logical to think that a gigantic star has far more fuel and should therefore live longer. However, the exact opposite is true. Very massive stars consume their nuclear fuel at an extraordinarily rapid rate because of the enormous pressures and temperatures within their cores. As a result, some exhaust all their energy in only a few million years. In contrast, small stars such as red dwarfs burn their fuel very slowly and can remain active for trillions of years, far longer than the current age of the universe. The most spectacular stars are also, paradoxically, among the most short-lived. We still do not know whether there is a limit to how large a black hole can become. Black holes with masses equivalent to billions of suns have been discovered at the centers of giant galaxies. However, astronomers continue investigating whether there is a maximum size imposed by the laws of physics or whether these objects can keep growing indefinitely as long as enough matter is available for them to absorb. Their growth depends on many factors, including the amount of available gas, mergers with other black holes, and the energy released during accretion, which can sometimes slow the infall of new material. Determining the true upper limit for these cosmic giants remains an open question. When we observe extremely distant galaxies, we are also witnessing the earliest chapters in the evolution of the universe. Light from some galaxies has traveled for more than 13 billion years before reaching our telescopes. This means that we see them as they were when the universe was only beginning to form its first generations of stars. Every new image of these objects allows scientists to reconstruct a different stage of cosmic history, showing how galaxies evolved from small, irregular structures into the enormous systems seen today. Modern telescopes not only explore vast distances, but also allow us to reconstruct the formation of the universe chronologically by observing different eras at the same time. Perhaps the greatest discovery of the future will not be finding a definitive answer, but asking an entirely new question. Throughout history, every major scientific breakthrough has opened doors that we had never imagined. The discovery of galaxies revealed the immensity of the universe. Cosmic expansion led to the study of the Big Bang. Gravitational waves introduced a new way of observing the cosmos. The instruments developed over the coming decades will likely discover phenomena that are impossible to anticipate today. The history of science shows that knowledge advances not only by answering questions, but also by uncovering completely unexpected ones. Perhaps the most fascinating mysteries of the universe are precisely those whose existence we do not yet even suspect. Some galaxies are so faint that they remained hidden for nearly the entire history of astronomy. In addition to the large spiral and elliptical galaxies that are easily visible, the universe contains ultra-diffuse galaxies whose stars are spread across enormous regions but have an extremely low surface brightness. Some are comparable in size to the Milky Way, yet contain hundreds of times fewer stars, making them very difficult to detect even with modern telescopes. Astronomers are still investigating how objects could become so large while remaining so dim. Some appear to be dominated by dark matter, while others display unexpected properties that challenge traditional models of galaxy formation. The universe may contain far more galaxies of this type than we have managed to discover. We still do not know how the first complex molecules in the universe managed to form. Shortly after the Big Bang, the cosmos was composed almost entirely of hydrogen and helium. Over time, the first stars began to appear, producing heavier elements such as carbon, oxygen, and nitrogen. However, scientists are still investigating how those elements eventually combine to form increasingly complex molecules inside extremely cold interstellar clouds. We now know that alcohols, simple sugars, and many organic molecules exist in space, but researchers are still trying to reconstruct the precise chemical sequence that allowed them to emerge. Understanding these processes is essential for explaining how the universe evolved from containing only simple elements to supporting the enormous chemical diversity observed in galaxies, planets, and star systems. Some black holes may remain hidden while emitting almost no detectable signal. Most black holes discovered so far were identified because they interact with nearby stars or produce intense emissions while absorbing matter. However, a completely isolated black hole would emit almost no radiation and would be nearly impossible to observe directly. Astronomers believe that millions of these silent objects may be wandering through the Milky Way without having been detected. Occasionally, they can only be discovered when their gravity slightly bends the light of a distant star through a phenomenon known as gravitational lensing. This means that an enormous population of invisible black holes may remain hidden within our own galaxy. Galaxies may exchange matter during encounters that last hundreds of millions of years. When two galaxies pass relatively close to one another, their enormous gravitational fields slowly begin to distort them. During this process, they can pull large amounts of gas, dust, and even stars away from each other, forming long tails that extend for hundreds of thousands of light years. Some of that material will eventually become part of the neighboring galaxy, while another portion will remain drifting through intergalactic space. These encounters are a normal stage of galactic evolution and have occurred countless times since the first few billion years of the universe. The Milky Way itself preserves evidence of ancient mergers with small galaxies that were absorbed long ago. Light can travel completely around a black hole before escaping into space. The extreme gravity of a black hole does not merely bend the path of light slightly, but can curve it so intensely that some photons travel in nearly complete orbits around the object before continuing on their journey. There is even a region known as the photon sphere, where gravity allows extremely unstable paths for light. Any slight disturbance causes the photons either to fall into the black hole or escape into space. This extraordinary behavior helps create the characteristic bright ring observed around certain black holes by telescopes, such as the Event Horizon Telescope. It is one of the most spectacular effects predicted by general relativity. We still do not know how frequently Earth-like planets form in our galaxy. Since the discovery of the first exoplanets, astronomers have identified thousands of worlds orbiting other stars. Some are similar in size to Earth and are located within the so-called habitable zone, where conditions may allow liquid water to remain on the surface. However, knowing their size and distance from their star is not enough to determine whether they are truly comparable to our planet. Their composition, atmosphere, geological activity, and magnetic field also play fundamental roles. Until we can study these characteristics in much greater detail, it will remain impossible to know how many truly Earth-like worlds exist in the Milky Way. The universe may contain countless stars that never formed planets. Although we now know that planetary systems are very common, there are still many stars around which no planets have been detected. Some may have lost the material required during their formation, while in others, gravitational processes may have prevented small bodies from growing into stable planets. It is also possible that some systems formed planets that were later ejected into interstellar space through gravitational interactions. Understanding why some stars develop complex planetary systems while others apparently do not is an important part of explaining the enormous diversity observed throughout our galaxy. Collisions between galaxies rarely destroy stars, but they profoundly transform galactic structure. Even though a galaxy can contain hundreds of billions of stars, the enormous distances between them make direct collisions extremely unlikely during a galactic merger. Instead, what truly interact are the immense gravitational fields and gigantic clouds of gas. These forces distort the galaxies, trigger intense bursts of star formation, and alter their orbits over hundreds of millions of years. Eventually, two spiral galaxies may merge to form a single, much larger elliptical galaxy. These processes are among the most spectacular and slowest events in the universe. Globular clusters preserve some of the oldest stars ever discovered. Orbiting many galaxies are dense spherical groups containing anywhere from tens of thousands to millions of stars. These structures, known as globular clusters, formed during the earliest stages of galactic evolution, and many of their stars are nearly 13 billion years old. Studying them allows scientists to reconstruct what conditions were like in the universe shortly after the birth of the first galaxies. Although these clusters have been observed for centuries, important questions remain about their origin, evolution, and the role they played during the formation of galaxies such as the Milky Way. The more we learn about the universe, the more we understand that our history is part of a much older story. The atoms that make up our bodies were born inside stars that disappeared billions of years ago. Our planet formed from a cloud of gas enriched by previous generations of suns. Earth orbits a star located in one spiral arm of a galaxy among hundreds of billions in the observable universe. However, even after understanding our cosmic origins in a level of detail that would have been unimaginable only a century ago, we still do not know what most of the universe is made of. The immensity of the cosmos reminds us that every discovery represents only a small step in an exploration that has barely begun. Some stars may be orbiting invisible black holes without us knowing it yet. Most black holes discovered so far are part of systems in which they absorb matter from a nearby star, producing intense X-ray emissions that make them easier to detect. However, there may also be numerous binary systems in which the black hole barely interacts with its companion star. In those cases, the only sign of its presence would be the orbital motion of the visible star, revealing the gravitational influence of a completely dark object. Thanks to space missions capable of measuring the movement of millions of stars with extraordinary precision, astronomers have begun identifying several promising candidates. Thousands or even millions of these systems may still remain hidden within the Milky Way, waiting to be discovered through increasingly precise observations. We still do not know how many galaxies truly exist in the observable universe. For decades, estimates suggested that there were around 100 billion galaxies. However, more recent studies indicate that the total number may have been much greater in the past because many small galaxies eventually merged to form larger ones. In addition, a vast number of extremely faint galaxies remain beyond the reach of current telescopes. As technology improves, astronomers continue discovering increasingly distant and less luminous systems, forcing them to revise earlier estimates constantly. Although the exact number remains uncertain, it is clear that the observable universe contains an extraordinary number of galaxies, many of which will never be studied in the level of detail possible for our own Milky Way. Matter we can see represents only a small part of the universe's total content. Everything we can observe directly, including stars, planets, nebulae, galaxies, and even our own bodies, is made of ordinary matter composed of protons, neutrons, and electrons. However, cosmological observations indicate that this type of matter accounts for only a small fraction of everything in the universe. Most of the total content consists of dark matter and dark energy, two components whose true nature remains unknown. This means that every visible object in the cosmos represents only a narrow window into a far greater reality. Paradoxically, after centuries of studying the universe, we still do not know the composition of most of everything that exists. The first stars may have been hundreds of times more massive than the Sun. Cosmological simulations indicate that conditions shortly after the Big Bang favored the formation of stars very different from those that exist today. Because only hydrogen and helium were present, enormous clouds of gas lost heat far less efficiently, allowing gigantic stars to form that may have reached hundreds of times the mass of the Sun. These stars would have lived for only a few million years before exploding or collapsing directly into black holes. Although none has ever been observed directly, scientists believe they played a decisive role in producing the first heavy elements and transforming the early universe. Finding evidence of these first generations of stars remains one of the major goals of modern astronomy. Galaxies can continue growing even when they form almost no new stars. Although a galaxy may have exhausted much of the gas needed to produce new stars, it can still increase in size by merging with smaller galaxies. During these gravitational encounters, it absorbs stars that already exist without needing to create new ones. As a result, some very old galaxies continue expanding slowly while maintaining relatively low levels of star formation. This silent growth has been confirmed through observations of both nearby and distant galaxies, allowing scientists to reconstruct part of their evolutionary history. Understanding the importance of these mergers is essential for explaining how the giant galaxies that dominate the universe today came into existence. There may be regions of the universe where no major galaxies ever formed. Matter is not distributed uniformly throughout the cosmos. Some areas contain enormous clusters and filaments filled with galaxies, while others remain extraordinarily empty. In regions where the initial density fluctuations were too small, gravity may never have gathered enough matter to build large galaxies. As a result, vast areas of the cosmos may contain only small, isolated galaxies, extremely diffuse gas, and dark matter. These regions serve as natural laboratories for studying how the universe's initial distribution of matter influenced its large-scale evolution. Light from a galaxy can reach us after traveling for longer than Earth has existed. Some galaxies observed by the most powerful telescopes emitted the light we receive today more than 13 billion years ago, when the universe was only beginning to form its first structures. In comparison, Earth is approximately 4.5 billion years old. This means that many of the photons captured by our telescopes began their journey long before the Sun, the planets, or any known form of life existed. Every deep observation of the universe creates a direct connection with events that occurred billions of years before the birth of our own planetary system. We still do not fully understand how gravity and quantum mechanics interact. General relativity describes the behavior of gravity in stars, galaxies, and black holes with extraordinary precision. Quantum mechanics, on the other hand, explains the behavior of the smallest known particles with equally remarkable accuracy. However, when both theories must be applied at the same time, as happens inside a black hole or during the earliest moments of the universe, deep mathematical incompatibilities appear. Resolving this conflict is one of the greatest challenges in modern physics. A future quantum theory of gravity may explain phenomena that currently remain completely beyond our understanding. Stars are not born in isolation, but within enormous stellar families. Most stars form inside gigantic molecular clouds, where hundreds or even thousands of new stars appear at nearly the same time. During their first few million years, they remain grouped in open clusters before slowly dispersing throughout the galaxy because of gravitational interactions. Scientists believe that the Sun itself was born alongside thousands of sibling stars approximately 4.6 billion years ago. Over time, those stars moved away along different orbits around the Milky Way. Today, astronomers are attempting to identify some of these possible solar siblings by analyzing their chemical composition and movements through the galaxy. Every generation of telescopes has revealed a universe larger than the previous one could imagine. When Galileo pointed his small telescope toward the sky, he discovered mountains on the Moon and moons orbiting Jupiter. Centuries later, far more advanced telescopes demonstrated that the Milky Way was only one among hundreds of billions of galaxies. Today, space and ground-based observatories allow scientists to study the early universe, detect gravitational waves, and analyze the atmospheres of planets located light-years away. However, history shows that every new instrument not only answers old questions, but also reveals completely unexpected mysteries. Future telescopes will most likely discover phenomena whose existence we do not even suspect today. Stars composed entirely of exotic matter that has not yet been discovered may exist. Known stars obtain most of their energy through the nuclear fusion of hydrogen and other light elements. However, some physical theories allow for the existence of far stranger objects made from states of matter that have not yet been confirmed experimentally. Among the proposed possibilities are so-called quark stars, in which the particles that normally form protons and neutrons would cease to exist as separate units because of extraordinary pressures. Other hypothetical objects made of still unknown forms of matter have also been proposed. So far, none has been identified with certainty, but future observations of extremely compact stars may reveal whether these objects truly exist. Their discovery would greatly expand our understanding of how matter behaves under the most extreme conditions in the universe. Light from a star can be bent by a galaxy located billions of light-years away. According to general relativity, gravity curves space-time, meaning that light does not always travel in a straight line when it passes through regions containing a large concentration of mass. This phenomenon, known as gravitational lensing, can cause a galaxy or galaxy cluster to act like a gigantic cosmic magnifying glass, amplifying the light from objects located much farther away. Thanks to this effect, astronomers have been able to observe some of the oldest galaxies ever detected. In some cases, multiple images of the same object appear, along with spectacular rings of light known as Einstein rings. Gravity itself, therefore, becomes a natural tool that allows us to explore regions of the universe that would otherwise remain invisible. We still do not know whether dark matter can form structures similar to visible galaxies. Dark matter appears to play a fundamental role in galaxy formation by providing the gravity needed to gather large amounts of ordinary matter. However, it remains unknown whether dark matter itself could form complex independent structures similar to galaxies made of stars. Some models suggest that, if its particles possess certain properties, completely dark halos or concentrations may exist where visible matter never formed. Because these objects would emit no light, they could only be detected through their gravitational effects on nearby galaxies or on the path of light. Confirming or ruling out this possibility would greatly improve our understanding of the true nature of dark matter. Stars can survive explosions that destroy their companions. Many stars form binary systems in which both objects orbit a common center for millions of years. If one of them explodes as a supernova, the other may survive and be thrown away at enormous speed because of the system's sudden loss of mass. Some stars observed today appear to have experienced exactly this type of event. Their extraordinary speed and certain chemical characteristics allow astronomers to reconstruct part of their history. Studying these objects helps scientists understand how multiple star systems evolve and how stars become distributed throughout the galaxy after some of the most energetic events in the universe. The universe may contain black holes that were never located inside a galaxy. When two galaxies collide, their supermassive black holes may eventually merge after millions of years of gravitational interaction. However, during that merger, the gravitational waves that are emitted can propel the resulting black hole at enormous speed if the radiation is released with even a slight asymmetry. In theory, some black holes could receive enough of a push to escape their galaxies completely and begin a solitary journey through intergalactic space. Although several candidates have already been identified, there is still no definitive confirmation of this phenomenon. If it truly occurs frequently, the universe may contain isolated supermassive black holes traveling between galaxies. We still do not know how the final stars in the universe will evolve. The smallest stars, known as red dwarfs, consume their fuel so slowly that they can remain active for trillions of years, far longer than the current age of the universe. None has yet had enough time to completely exhaust its hydrogen since the Big Bang. This means that the universe is still too young for astronomers to have observed the natural end of a red dwarf's life. Their future evolution can only be studied through theoretical models. In an unimaginably distant future, these stars will mark the final stages of the stellar era before the universe becomes progressively darker and colder. Galaxies can contain immense rivers of stars flowing through them. Thanks to increasingly precise observations, astronomers have discovered long stellar streams made up of thousands of stars moving together around the galaxy. Many are the remains of ancient dwarf galaxies or star clusters that were slowly torn apart by the gravity of the Milky Way. These streams preserve information about gravitational encounters that occurred billions of years ago and allow scientists to reconstruct part of our galaxy's history. By analyzing their paths, researchers also obtain clues about the distribution of dark matter in the galactic halo, making these stellar rivers an exceptional tool for studying invisible regions of the universe. Planets can survive the death of their star for billions of years. When a star similar to the Sun exhausts its fuel, it expels much of its outer layers and eventually becomes a white dwarf. Some of its planets may be destroyed during this process, but others survive and continue orbiting the small stellar remnant for extremely long periods. Scientists have even found evidence of fragments from ancient planets falling onto white dwarfs, allowing them to indirectly analyze the composition of those vanished worlds. These discoveries show that the evolution of a planetary system can continue long after the death of its central star. We still do not know how many intermediate mass black holes exist. For a long time, astronomers recognized two major categories of black holes: stellar mass black holes, formed by the collapse of massive stars, and supermassive black holes, found at the centers of most galaxies. However, a population of black holes with intermediate masses should exist between these two groups. Finding them has proved surprisingly difficult because they produce few observable signals. In recent years, several promising candidates have been identified through gravitational wave observations and studies of star clusters, but scientists still do not know how common they truly are. Solving this mystery would help explain how the gigantic black holes that dominate galactic centers manage to grow. The more deeply we explore the universe, the more apparent it becomes that we still know only a small part of its history. In just a few decades, humanity has learned that galaxies evolve, space expands, planets exist around other stars, and space-time itself can vibrate in the form of gravitational waves. However, we still do not understand the nature of dark matter, the origin of dark energy, the behavior of quantum gravity, or what happened during the earliest moments of the universe. Every answer opens new questions, and every generation of instruments discovers phenomena that once seemed unimaginable. Everything suggests that astronomy's greatest discoveries still belong to the future, and that the universe holds an immense number of secrets waiting to be revealed. There is a type of galaxy that appears to awaken after long periods of apparent inactivity. Many galaxies spend millions or even billions of years forming very few stars and displaying relatively little activity. However, under certain circumstances, a collision with another galaxy or the arrival of large amounts of gas can intensely reactivate their evolution. These episodes trigger true bursts of star formation, during which thousands of new stars are born within a relatively short interval from an astronomical perspective. Scientists continue investigating which conditions are required to initiate these bursts and how long they can remain active. Understanding this phenomenon is essential for reconstructing the evolutionary history of galaxies and explaining why some appear to be reborn after remaining almost inactive for immense periods of time. We still do not know exactly what the universe was like before the first galaxies appeared. Current observations allow scientists to study regions very close to the beginning of cosmic history, but there is an interval about which relatively little is still known. During that period, the universe was filled with hydrogen, helium, and dark matter, while small variations in density slowly began to grow under the influence of gravity. Over time, those tiny irregularities gave rise to the first stars and later to the first galaxies. However, many details about this transition remain unresolved. New space telescopes are beginning to reveal increasingly ancient objects, allowing astronomers to reconstruct one of the least understood chapters in the evolution of the cosmos with greater precision. Black holes can influence regions located thousands of light-years away. Although their event horizons occupy relatively small regions compared with an entire galaxy, supermassive black holes can affect enormous volumes of space through the energy released as they absorb matter. In some cases, they produce gigantic jets of particles that travel at nearly the speed of light and extend across hundreds of thousands of light-years before losing intensity. These jets heat the surrounding gas, alter the formation of new stars, and can even change the evolution of entire galaxies. It is remarkable that an object whose central region may be smaller than the solar system can influence distances millions of times greater. There may be planets that have remained habitable for billions of years longer than Earth. The Sun is approximately halfway through its life as a main sequence star. However, much less massive stars, such as red dwarfs, consume their fuel extremely slowly. Some will remain stable for trillions of years, providing their planets with a constant supply of energy for periods far longer than the current age of the universe. If any of those worlds have the right conditions, life could have vastly more time to evolve than it has had on Earth. Although we still do not know whether ecosystems of this kind truly exist, they represent one of the most fascinating possibilities in the search for life beyond the solar system. Gravitational waves could help us discover completely unknown phenomena. Until only a few years ago, astronomy depended almost entirely on light to study the universe. However, the direct detection of gravitational waves introduced an entirely new field of research. Unlike light, these waves pass through almost any obstacle without being absorbed, carrying direct information about the processes that generated them. As detectors become more sensitive, they may record events that have never been observed before, including mergers between exotic objects, signals from the early universe, or phenomena that we cannot yet even imagine. The history of astronomy shows that every new way of observing the cosmos eventually leads to unexpected discoveries, and everything suggests that gravitational wave astronomy will follow the same path. We still do not know whether there is a hidden pattern in the distribution of galaxies. On the largest scales, galaxies form an immense network of filaments and voids whose structure originated from small fluctuations present shortly after the Big Bang. However, some studies continue investigating whether additional regularities or alignments exist that could reveal physical processes that are still unknown. Most observations agree with the standard cosmological model, but as galaxy catalogs expand, new opportunities arise to test those predictions with greater precision. Understanding exactly how galaxies are arranged across the largest scales will provide deeper insight into the nature of dark matter and the evolution of the universe from its first millions of years. Some stars are born surrounded by dozens of potential planets before most of them disappear. When a young star forms, it remains surrounded by an enormous disk of gas and dust in which countless small bodies called planetesimals begin to appear. Over millions of years, these objects collide, break apart, and repeatedly combine again. Only a small fraction survives long enough to become stable planets, while the rest falls into the star, is expelled from the system, or becomes incorporated into larger bodies. The final result depends on countless, extremely complex gravitational interactions. Every planetary system represents the unique outcome of a chaotic process that began with billions of small fragments orbiting a newly formed star. Milky Way may merge with small galaxies even before it encounters Andromeda. Our galaxy does not evolve in isolation. Numerous dwarf galaxies orbit around it and are slowly moving closer because of gravity. Some already show clear signs of being torn apart by the Milky Way's gravitational forces, leaving long streams of stars spread throughout the galactic halo. This process will continue for billions of years and gradually alter the structure of our galaxy long before the major collision predicted with Andromeda. The history of the Milky Way is, to a great extent, the history of countless mergers with much smaller systems. We still do not know how many potentially habitable worlds remain hidden around very faint stars. Current methods for detecting exoplanets work best when the planets are large or when they orbit relatively bright stars. However, the smallest and dimmest stars make up the majority of stars in the galaxy. Rocky planets that are difficult to detect with current technology may exist around many of them. As telescopes become more precise, astronomers hope to discover a much larger population of small worlds that have so far gone unnoticed. Some could become priority candidates for future searches for possible signs of life. Every generation of scientists has discovered that the universe is more complex than the previous one could imagine. What began as the observation of a few points of light in the sky has evolved into an exploration of black holes, dark matter, dark energy, gravitational waves, exoplanets, and galaxies located billions of light-years away. However, the more our knowledge grows, the more apparent it becomes that we understand only a small part of reality. Instruments continue improving, theories are refined, and every new discovery expands the range of unanswered questions. Everything suggests that the universe still holds countless secrets, and that the coming decades may once again transform our understanding of the cosmos in ways we can barely imagine today. There is a region around some black holes where space itself appears to be dragged along. When a black hole spins on its axis, it not only distorts space-time through its enormous gravity, but also pulls it around through a phenomenon known as frame dragging. The region where this effect becomes dominant is called the ergosphere. Inside it, no object can remain completely motionless relative to the distant universe because space itself is being dragged by the black hole's rotation. Some models indicate that it may be possible to extract part of a black hole's rotational energy through physical processes occurring within this region. Although these ideas are difficult to test directly, they represent one of the most remarkable predictions of general relativity and remain the subject of intense research. We still do not know why some stars produce explosions far more powerful than those of other apparently similar stars. When certain massive stars reach the end of their lives, they explode as supernovas. However, there are extraordinary events known as superluminous supernovas whose brightness can exceed that of a conventional supernova by dozens of times. Astronomers continue debating which mechanisms allow such enormous amounts of energy to be released. Some hypotheses point to newly formed magnetars capable of injecting additional energy into the explosion, while others suggest interactions with enormous layers of gas previously expelled by the star. Every new event observed provides valuable information, but the exact origin of these extreme explosions remains one of the major mysteries of stellar evolution. Dark matter may be passing through Earth at this very moment without leaving almost any trace. If current theories are correct, our galaxy is immersed in an immense halo of dark matter that surrounds it completely. As Earth moves around the galactic center, it continuously travels through this invisible halo. This means that enormous amounts of dark matter may constantly be passing through our planet and our own bodies without us noticing. The reason is that, as far as we know, dark matter barely interacts with ordinary matter except through gravity. Detecting it directly represents one of the greatest challenges in experimental physics, and numerous laboratories around the world continue searching for extremely faint signs of its presence. Most distant galaxies allow us to observe an era when the universe had only begun to organize itself. Images of the most remote objects show a cosmos very different from the one we see today. Instead of large, clearly defined spiral galaxies, small, irregular structures dominated, growing rapidly through continuous mergers. Many contained intense bursts of star formation and black holes that were gaining mass at extraordinary speed. Observing this period is essential for understanding how modern galaxies emerged. Every new detection of an extremely distant galaxy provides another snapshot of one of the most dynamic eras in the entire history of the universe. We still do not know whether planets completely covered by permanent clouds exist. Studies of exoplanets indicate that some worlds may possess atmospheres so dense that their surfaces remain hidden beneath a continuous layer of clouds throughout their entire existence. In these cases, light from the star would barely penetrate the lower layers of the atmosphere. Depending on their composition, those clouds could be made of water, sulfuric acid, vaporized silicates, or even condensed metals on the hottest planets. Although cloud-rich atmospheres have already been detected on several exoplanets, we are still far from knowing in detail what their landscapes would look like beneath those dense envelopes. Black holes could help reveal the existence of new fundamental particles. Some theories propose that certain extremely light particles that have not yet been discovered could interact with rotating black holes through highly specific quantum processes. If this occurred, they would gradually affect the black hole's rotation rates, leaving signals that might be detected through astronomical observations. In this way, black holes would act as enormous natural laboratories capable of testing theories that are impossible to verify using particle accelerators on Earth. Although these ideas remain within the realm of theoretical research, they demonstrate how the most extreme phenomena in the universe can become tools for studying the fundamental laws of nature. Oldest stars preserve information about a universe that no longer exists. Some stars formed more than 13 billion years ago continue shining today in the Milky Way's halo. Because they were born when the universe was very young, they contain extremely small amounts of heavy elements, reflecting the chemical composition that existed shortly after the first generations of stars. By carefully analyzing their composition, astronomers can reconstruct how the universe evolved during its first few 100 million years. These ancient stars serve as true cosmic fossils, allowing scientists to study an era that cannot be observed directly. Habitable moons may exist around giant planets located beyond the solar system. So far, most searches for life have focused on rocky planets similar to Earth. However, some scientists believe that large moons orbiting gas giants could also provide suitable conditions for liquid water and a stable atmosphere. In our own solar system, several moons contain oceans hidden beneath thick layers of ice, demonstrating that such environments are possible. If even larger moons orbit giant exoplanets, some could become especially favorable places for life to emerge. Although none has yet been definitively confirmed, they represent some of the most promising targets for future missions searching for habitable worlds. We still do not know whether the first galaxies grew mainly through mergers or through the continuous accumulation of gas. Both processes appear to have contributed to the development of early galaxies, but astronomers continue investigating which one dominated during the universe's earliest stages. Some observations show frequent collisions between small young galaxies, while others reveal enormous streams of gas slowly falling into them from the cosmic web. Both mechanisms may have operated simultaneously in different regions of the universe. Determining which was more important will help scientists better understand how the enormous galaxies we observe today came into existence. Every answer we obtain about the cosmos expands the size of the unknown. Only a century ago, we did not even know that galaxies existed beyond the Milky Way. Today, we know of billions of them, have detected gravitational waves, photographed black holes, discovered thousands of exoplanets, and observed galaxies whose light began its journey shortly after the birth of the universe. However, we still do not know what most of the cosmos is made of, how the first structures emerged, what happened during the first instant of time, or whether we are alone in the universe. The history of astronomy shows that every major discovery marks not the end of a search, but the beginning of new and even deeper questions. Some galaxies may conceal black holes that have never begun feeding actively. Most supermassive black holes discovered so far were identified because they absorb large amounts of gas, releasing enormous quantities of energy that illuminate the centers of their galaxies. However, astronomers believe that many galaxies contain nearly inactive black holes that capture very little matter. These silent giants can remain dormant for millions of years without producing intense emissions, making them extremely difficult to detect. Their presence can only be inferred by studying the movement of nearby stars. The universe probably contains far more dormant supermassive black holes than active ones, waiting for a new cloud of gas to reactivate their extraordinary activity. We still do not know whether the universe produced new galaxies at the same rate throughout every period of its history. Observations show that there was an era known as cosmic noon, when star formation and galaxy growth reached their highest levels approximately 10 billion years ago. Since then, average activity has gradually declined. However, scientists continue investigating why this change occurred and which factors were responsible for reducing the rate at which new stars formed. Understanding this transition will make it possible to reconstruct the evolution of the universe more precisely, from its most active stages to the relatively quiet state we observe today. Gravity can act as a gigantic natural telescope, capable of revealing objects that would otherwise be impossible to observe directly. When a massive galaxy or galaxy cluster lies directly between Earth and a much more distant object, its gravity curves space-time and concentrates the light from the object behind it. This effect can amplify its brightness by dozens or even hundreds of times, allowing astronomers to detect extremely ancient galaxies that would normally remain beyond the reach of our telescopes. Thanks to these gravitational lenses, scientists have observed some of the earliest structures formed after the Big Bang. In a sense, the universe builds enormous telescopes using gravity alone. Some stars may become black holes without producing a detectable explosion. Scientists traditionally believed that very massive stars had to explode as supernovas before forming black holes. However, several models indicate that certain stars may collapse directly when their cores can no longer support themselves, disappearing almost completely without generating a bright explosion. In these cases, the star would simply stop emitting light while the newly formed black hole took its place. Detecting this process is extremely difficult, precisely because it produces almost no visible signal. If it occurs frequently, a significant portion of the universe's black holes may have formed through these silent disappearances. We still do not know how many rogue planets travel between the stars of our galaxy. Planetary systems often experience complex gravitational interactions during their formation. In some cases, encounters between giant planets can completely eject other worlds into interstellar space. These rogue planets no longer orbit any star and travel through the galaxy in complete darkness. Some studies suggest that billions of them may exist in the Milky Way alone, although most remain invisible because they reflect almost no light. Detecting them represents an enormous observational challenge, but every new discovery strengthens the idea that the space between stars may be filled with solitary worlds. Galaxies contain immense magnetic fields whose origin we still do not fully understand. In addition to stars, gas, and dark matter, many galaxies possess extensive magnetic fields that extend through their disks and halos. These fields influence the movement of charged particles, star formation, and various physical processes involving interstellar gas. However, astronomers are still investigating how they first emerged and how they have managed to persist for billions of years. Some theories propose that they began extremely weak and were gradually amplified by the movement of galactic gas. Solving this mystery will help scientists better understand the internal evolution of galaxies. Liquid oceans may exist, hidden inside planets completely covered by ice. Not every habitable world needs to possess visible seas like those on Earth. If a planet has enough internal heat generated by radioactive elements or gravitational forces, it could maintain enormous liquid oceans beneath a thick frozen crust for billions of years. Several moons in the solar system probably contain this type of underground ocean, proving that such environments are physically possible. If similar conditions occur around other stars, the number of places potentially favorable for life could be far greater than scientists imagined only a few decades ago. Stars are born inside clouds so dense that their own light takes time to escape. Before becoming fully visible stars, enormous concentrations of gas and dust slowly collapse under the force of gravity. During this early stage, the surrounding cloud is so thick that it absorbs much of the light emitted by the young protostar, concealing it from optical telescopes. Only infrared and radio observations can penetrate those dense layers of dust and directly study stellar birth. Using these techniques, astronomers have observed protoplanetary disks, jets of gas, and some of the earliest steps in the formation of planetary systems. We still do not know what the first black hole in the universe was. The earliest black holes began forming shortly after the birth of the first stars, but scientists are still investigating their exact origin. Some may have emerged from the collapse of gigantic stars belonging to the first stellar generation. Other models propose that certain extremely massive clouds of gas collapsed directly without first forming stars. Solving this question will help explain how the supermassive black holes observed when the universe was still very young came into existence. Every new observation of primordial galaxies provides additional clues about this fascinating chapter of cosmic history. The universe has shown again and again that reality exceeds every human expectation. Each technological advance has revealed phenomena that once appeared impossible: invisible galaxies, black holes, planets around other stars, gravitational waves, dark matter, and cosmic structures of unimaginable size. However, all these discoveries represent only a small part of a universe that remains mostly unknown. Every new observation expands our knowledge, but also makes the enormous number of unanswered questions even more apparent. Perhaps the most extraordinary lesson offered by the cosmos is that there is always something beyond what we believe we understand, waiting for human curiosity to discover it. There is a mysterious natural limit that prevents stars from reaching just any size. Although the universe contains stars far more massive than the Sun, astronomers have not found stars with arbitrarily large masses. Observations suggest that there is an approximate limit near 200 solar masses, although its exact value remains under investigation. When an extremely massive star begins to form, the intense radiation it produces exerts enormous pressure on the surrounding gas, making it difficult for the star to continue accumulating matter. As a result, the star's own brightness eventually slows its growth. However, scientists are still studying whether this limit can be exceeded under exceptional conditions, especially in the early universe. Understanding why stars appear to stop growing is an important part of explaining the evolution of galaxies and the formation of the most extreme objects in the cosmos. We still do not know how the Milky Way will evolve after merging with Andromeda. Simulations indicate that the two galaxies will begin interacting in approximately 4.5 billion years and will eventually form a single, much larger galaxy. However, the exact details of the final result remain uncertain. Depending on the amount of available gas, the influence of satellite galaxies, and the activity of the central black holes, the new galaxy may have a structure very different from any seen today. Over billions of years, enormous streams of stars, intense episodes of star formation, and profound gravitational reorganizations will occur. Although the general outcome appears relatively clear, many aspects of this future transformation remain under study. Some cosmic explosions can continue shining for years after the initial event. When a supernova or gamma-ray burst releases enormous amounts of energy, the explosion does not always end after only a few days. The ejected material continues expanding and may collide with the interstellar gas surrounding the star. These collisions generate shock waves that continue producing radiation for months, years, or even centuries. By analyzing this delayed light, astronomers can reconstruct the characteristics of the original explosion and the environment in which it occurred. In some cases, the remains of ancient supernovas remain visible for thousands of years, allowing scientists to study events that occurred long before the birth of modern civilization. The ordinary matter in the universe is distributed in far more complex ways than scientists once imagined. For a long time, it was believed that most visible matter was concentrated within stars and galaxies. However, recent observations show that a large fraction is spread out as extremely hot, thin gas between galaxies, following the enormous filaments of the cosmic web. This material is very difficult to detect because it emits very little light, but it plays a fundamental role in galactic growth and in transporting chemical elements throughout the universe. Locating all this ordinary matter has required decades of observations and remains an important area of research. We still do not know how magnetic fields affect the birth of the first stars. Gravity is the main driving force behind star formation, but it does not act alone. Magnetic fields inside molecular clouds also influence the movement of gas, the speed of collapse, and the formation of protoplanetary disks. However, measuring these fields is extraordinarily difficult because of the enormous distances and the complexity of the regions where stars are born. Astronomers are constantly developing new observational techniques to better understand how gravity, magnetism, and turbulence interact during the first few million years of a star's life. Galaxies can completely change their appearance over time. A gas-rich spiral galaxy can slowly transform into an elliptical galaxy after multiple mergers with other galaxies. During this process, the elegant spiral arms disappear, stellar orbits are reorganized, and the formation of new stars decreases considerably. What we observe today as a quiet elliptical galaxy may have been, billions of years ago, a spiral system filled with active regions where stars were constantly being born. Galaxies are not permanent structures, but dynamic systems that evolve continuously throughout the history of the universe. Planetary systems may exist whose stability depends on a delicate balance among several stars. Although our solar system orbits a single star, many stellar systems contain 2, 3, or even more suns orbiting one another. In some of these systems, planets manage to maintain stable orbits for billions of years, while in others, small gravitational variations can completely alter their paths. Astronomers continue discovering new examples that reveal an enormous diversity of orbital configurations. These findings demonstrate that the architecture of planetary systems can be far more varied than the example provided by our own cosmic neighborhood. We still do not know the ultimate fate of all the matter dispersed between galaxies. Some of the gas floating through intergalactic space will eventually fall toward galaxies because of gravity, fueling the formation of future generations of stars. Another portion will remain hot for billions of years or be expelled even farther by the activity of supermassive black holes and stellar explosions. Understanding how this immense reservoir of matter continuously circulates is essential for explaining why some galaxies continue growing while others almost completely stop evolving. The universe constantly recycles its matter through processes that we are only beginning to understand in detail. Future telescopes may directly observe the birth of the first black holes. Current instruments already allow astronomers to study galaxies that formed when the universe was only a few 100 million years old. However, the next generations of space and ground-based observatories will be even more sensitive and may detect signals from still earlier periods. If this happens, astronomers will be able to compare different theories about the origin of the first black holes directly and reconstruct one of the most important chapters in cosmic history in far greater detail. Every technological improvement brings us a little closer to witnessing events that occurred almost at the beginning of time. Perhaps the universe never stops surprising us because we always observe it from a limited perspective. Our species lives on a small planet orbiting an ordinary star located near the outskirts of an average galaxy. From this tiny corner, we have managed to discover the expansion of the universe, detect gravitational waves, photograph black holes, and explore thousands of exoplanets. However, all this knowledge comes only from the small region of the cosmos that we can observe. Beyond the observable horizon, phenomena, structures, or even physical laws may exist that we will never be able to study directly. Perhaps the most extraordinary mystery of the universe is that, no matter how much we learn about it, an immensely greater portion will always remain beyond our reach. Some galaxies release enough energy to alter the growth of other nearby galaxies. When a supermassive black hole enters a period of intense activity, it can release enormous amounts of radiation and launch jets of particles that travel for hundreds of thousands of light years. In galaxy clusters, this energy affects not only the galaxy containing the black hole, but also the hot gas shared throughout the entire cluster. By heating this material, it becomes more difficult for the gas to cool and collapse to form new stars in nearby galaxies. Astronomers continue studying the extent to which this mechanism influences the evolution of entire galaxies. It is remarkable that a single black hole can indirectly affect the development of stellar systems located at enormous distances. We still do not know exactly what the first planets in the universe were like. The earliest planetary systems must have formed after the first generations of stars had already enriched space with elements heavier than hydrogen and helium. However, those first planets were probably very different from the ones that exist today because the universe contained much smaller amounts of iron, silicon, oxygen, and other elements essential for forming rocky worlds. Scientists are investigating how this primitive chemical composition influenced the birth of the first planets and what characteristics they may have possessed. Discovering extremely ancient planetary systems will help explain how the diversity of worlds evolved throughout cosmic history. Black holes can remain completely invisible for millions of years before becoming active again. A black hole only releases large amounts of energy when enough matter is available for it to absorb. If the surrounding gas disappears, the object enters a long period of inactivity during which it produces almost no detectable radiation. However, a new cloud of gas, the approach of a star, or a galactic collision can reactivate the accretion process. In only a few million years, an apparently silent black hole can become one of the brightest objects in the universe. This alternation between active and inactive periods explains why some galaxies have extremely luminous cores, while others contain nearly undetectable black holes. Stars can form true cosmic cities where millions of them remain extremely close together. Globular clusters are among the densest stellar environments known. In their central regions, stars can be hundreds of times closer together than they are in the Sun's neighborhood. Despite this enormous concentration, direct collisions remain relatively rare because of the immense speeds and distances involved. However, the intense gravitational interactions encourage the formation of exotic binary systems, pulsars, and other extraordinary objects. These ancient clusters serve as natural laboratories for studying stellar evolution under extreme conditions. We still do not know how many wandering black holes travel through the space between galaxies. Galactic collisions and complex gravitational interactions can eject black holes from their original galaxies. Some may be small remnants of ancient stars, while others could reach enormous masses if they were expelled after supermassive black holes merged. Without nearby stars to fuel their activity, these cosmic travelers would remain almost completely invisible. Detecting them will require carefully observing their gravitational effects on light or on objects passing near them. Intergalactic space may contain a population of completely isolated black holes that we have not yet managed to identify. The cosmic web continues growing slowly even today. The enormous filaments of galaxies that now extend across the observable universe emerged from tiny fluctuations present shortly after the Big Bang. Although the formation process was far more intense during the first few billion years, gravity continues slowly reorganizing matter. Galaxies are still falling toward gigantic clusters. Filaments are gaining mass, and new mergers are constantly altering the architecture of the cosmos. The evolution of the universe did not end billions of years ago. It continues unfolding at this very moment, although at a rate imperceptible during a human lifetime. Exoplanets may exist where the seasons last for entire centuries. The duration of the seasons depends on many factors, including the tilt of a planet's axis, the shape of its orbit, and the behavior of its star. In some planetary systems, orbits are far more elongated than Earth's, causing enormous temperature differences between different parts of the year. If the orbital period is also very long, a single season could last for decades or even centuries. Although we currently know of few examples in enough detail to confirm these conditions, astronomical models show that they are physically possible. This demonstrates that the enormous diversity of discovered planets probably includes climates unlike anything experienced on Earth. The most massive stars enrich the universe much sooner than smaller ones. Because they consume their fuel extremely quickly, giant stars live for only a few million years before exploding as supernovas. These explosions scatter large quantities of heavy elements into space, allowing later generations of stars to form rocky planets and other bodies rich in complex materials. In contrast, Smaller stars, such as the Sun, release much of their material far more slowly after billions of years of evolution. As a result, the shortest-lived stars played a decisive role during the earliest stages of the universe's chemical enrichment. We still do not know whether completely unknown physical processes operate inside black holes. Current theories describe the behavior of matter before it crosses the event horizon with great precision, but they leave many questions unanswered about what happens afterward. Solving this problem will probably require a theory that unifies general relativity with quantum mechanics. Some models propose that space-time develops entirely new properties under these extreme conditions, while others suggest that the classical singularities predicted by relativity disappear. For now, none of these ideas has been experimentally confirmed. The interior of a black hole remains one of the most mysterious places that physics is attempting to understand. The more deeply we explore the universe, the more we realize that our capacity for amazement is far from exhausted. Only a few generations ago, concepts such as black holes, exoplanets, dark matter, and gravitational waves belonged mainly to the realm of hypotheses. Today, they are part of modern astronomy, thanks to direct observations and technologies that would have been unimaginable a century ago. However, recent discoveries have also revealed that we still do not know the nature of most of the cosmos and that some of the most important questions remain unanswered. The history of space exploration shows that every answer expands the horizon of the unknown even further, reminding us that the universe probably holds secrets far more extraordinary than anything we can currently imagine. The universe may contain galaxies that will never be observed from Earth. Because space is expanding at an accelerating rate, some regions are so distant that light emitted by their galaxies will never reach us, no matter how much time passes. These galaxies lie far beyond our observable horizon and will remain completely inaccessible to any telescope built by humanity. This means that the real universe may contain an immensely greater number of galaxies than we will ever be able to study directly. Paradoxically, most of the cosmos may remain hidden not because of technological limitations, but because of the laws governing the expansion of space itself. We still do not know how dark matter affected the birth of the first stars. Cosmological models indicate that dark matter began clustering before ordinary matter, forming enormous gravitational halos that acted as invisible frameworks where gas later accumulated. However, scientists are still investigating exactly how this initial distribution influenced the size, number, and evolution of the earliest stars. Understanding this relationship will make it possible to reconstruct the first few 100 million years of cosmic history in greater detail and explain why galaxies began forming precisely where they did. Black holes may act as true archives of their galaxies' histories. Although a black hole does not preserve objects in an accessible form, its mass, rotation rate, and surroundings contain information about the events it has experienced over billions of years. Every episode of accretion, every merger with another black hole, and every interaction with surrounding gas slowly changes its properties. By analyzing these changes, astronomers can reconstruct part of the evolution of the galaxy that contains it. In a sense, a supermassive black hole preserves the accumulated imprint of countless processes that have occurred since the earliest stages of its galaxy. Stars can be born in regions where an explosion previously destroyed other stars. The universe constantly recycles its matter. When a supernova expels enormous quantities of gas enriched with heavy elements, that material eventually mixes with other interstellar clouds. Over millions of years, gravity gathers part of that gas again until new generations of stars form. As a result, a region devastated by a stellar explosion can become, much later, a brilliant nursery where hundreds of new stars are born. This cycle of destruction and renewal has occurred repeatedly since the first few billion years of the universe and continues taking place in many galaxies. We still do not know how many planetary systems remain intact throughout the entire lives of their stars. Many planets experience orbital migration, gravitational encounters, and even ejection during the first few million years of a planetary system's evolution. In other cases, the original architecture remains surprisingly stable for billions of years. Astronomers continue studying thousands of exoplanets to understand which factors determine the long-term stability of a system. The diversity discovered so far demonstrates that every star may develop a completely different planetary history. Giant galaxies continue capturing smaller galaxies even today. Gravity maintains a slow but constant process of galactic growth. Numerous dwarf galaxies orbit much larger systems until, after millions or billions of years, they are eventually absorbed. During this process, they leave behind enormous streams of stars that can surround the main galaxy like scars from ancient mergers. The Milky Way contains several of these streams, demonstrating that it continues growing through the gradual incorporation of smaller systems. This mechanism has played a decisive role in building the giant galaxies observed in the universe today. Planets may exist with atmospheres that change completely in composition from one season to another. On Earth, the seasons produce relatively moderate variations in climate. However, some exoplanet models indicate that worlds with highly eccentric orbits could experience extreme temperature changes capable of profoundly altering their atmospheres. Certain gases could condense during one part of the year and evaporate again months or decades later, significantly changing the atmospheric composition. Although such an extreme case has not yet been observed directly, future generations of telescopes may detect these types of variations on distant planets. We still do not know whether the oldest black holes in the universe continue to exist. The first black holes formed after the birth of the earliest stars may have continued growing for billions of years through mergers and the accretion of matter. However, some may also have remained relatively small until the present day. Identifying these ancient survivors would allow scientists to directly study a population formed very close to the beginning of cosmic history. Astronomers continue searching for objects that preserve characteristics consistent with an extremely early origin. Galaxies appear to evolve according to surprisingly similar rules despite their enormous diversity. Spiral, elliptical, irregular, and many other types of galaxies exist, ranging in size from a few million to several trillion stars. However, many follow very precise relationships between their mass, luminosity, rotation speed, and stellar content. These regularities indicate that, despite the immense complexity of the processes involved, common physical laws govern galactic evolution. Understanding the origin of these relationships remains one of the most important tasks in modern astronomy. Perhaps the greatest privilege of our time is living in an era when immense mysteries still remain to be discovered. Future generations will have more powerful telescopes, more sensitive detectors, and more complete theories than those available today. They will discover new planets, observe even more distant galaxies, and probably answer some of the questions that currently remain unresolved. However, they will also uncover new mysteries to replace the old ones. The history of science shows that knowledge never reaches a final point. Every answer expands our understanding of the universe, but also reveals entirely new horizons that invite us to continue exploring the cosmos without ever losing our sense of wonder at everything that remains hidden. The universe may be filled with tiny galaxies that have never managed to form many stars. In addition to the large galaxies visible through conventional telescopes, cosmological models predict an enormous population of small galaxies dominated almost entirely by dark matter. Many may have been unable to retain enough gas to produce large numbers of stars, causing them to emit very little light. Some have already been discovered orbiting the Milky Way, but astronomers believe they represent only a small fraction of those that truly exist. Locating these systems is essential for testing predictions about dark matter and understanding how the universe's earliest structures evolved. Thousands of extremely faint galaxies may remain hidden around our own. We still do not know whether black holes exist that have remained almost unchanged since the first few billion years of the universe. Most known black holes have slowly grown by absorbing matter or merging with other black holes. However, some may have remained isolated throughout nearly all of cosmic history, preserving masses very similar to those they had when they first formed. If scientists could identify them, they would provide a unique opportunity to directly study the conditions that existed during the universe's earliest stages. Finding these ancient survivors is one of the goals of future astronomical observations. The hottest stars emit much of their energy in forms of light that our eyes cannot see. The human eye detects only a small portion of the electromagnetic spectrum known as visible light. However, many extremely hot stars release most of their energy as ultraviolet radiation, while other regions of the universe shine mainly in X-rays, infrared light, or radio waves. Thanks to specialized telescopes capable of observing all these wavelengths, astronomers have discovered phenomena completely invisible to human vision, such as regions of intense star formation hidden behind clouds of dust and enormous jets of particles emitted by black holes. The universe contains far more colors than our senses can perceive. Galaxies can take hundreds of millions of years to recover after a major collision. When two galaxies pass through one another, most of their stars continue moving without colliding directly. However, the enormous gravitational disturbances profoundly alter stellar orbits and compress large amounts of gas, triggering intense episodes of star formation. After the initial encounter, a long process of reorganization begins that may continue for hundreds of millions or even billions of years. Only after this immense interval do the resulting galaxies reach a relatively stable structure. Galactic evolution occurs so slowly that no human being could directly observe a complete transformation. We still do not know whether some exoplanets have continents and oceans distributed in ways similar to those on Earth. Current instruments allow scientists to estimate the size, mass, and, in some cases, the approximate atmospheric composition of certain exoplanets. However, we still lack the resolution necessary to distinguish mountains, seas, or continents directly on their surfaces. Future generations of telescopes may analyze the small variations in brightness produced as these worlds rotate and obtain clues about the distribution of oceans and exposed land. Confirming the existence of a planet with geography similar to Earth's would represent one of the most important discoveries in modern astronomy. Black holes can alter the paths of stars located at enormous distances from their centers. Although the event horizon occupies a relatively small region, the gravitational influence of a supermassive black hole extends much farther. At the center of the Milky Way, for example, numerous stars follow extremely rapid orbits around the black hole known as Sagittarius A. Detailed study of these movements has made it possible to test the predictions of general relativity with great precision. The more precise the observations become, the more information scientists obtain about one of the most mysterious objects in the universe. The first galaxies were probably far more turbulent than those seen today. In the early universe, mergers between small galaxies and enormous streams of gas fueled extremely rapid growth. As a result, many young galaxies displayed chaotic motion, intense bursts of star formation, and irregular structures that are difficult to compare with the elegant spiral galaxies observed today. Over billions of years, these continuous interactions gradually stabilized many of them. Observing extremely distant galaxies allows astronomers to directly witness that era of intense activity and better understand how the universe evolved into its present appearance. We still do not know how many planetary systems have configurations completely unlike any known example. Since the discovery of the first exoplanets, astronomers have found giant planets orbiting extremely close to their stars, systems with multiple planets locked in gravitational resonance, and worlds that complete an orbit in only a few hours. Every new discovery demonstrates that nature can construct planetary systems in many different ways. Completely unexpected orbital configurations may still exist that have not yet been detected because of the limitations of current observational methods. The matter in the universe has been continuously recycled for billions of years. The atoms that now form stars, planets, and living beings have previously passed through countless stages. Many were created inside ancient stars, expelled through supernovas, incorporated into new clouds of gas, and eventually reused to form later generations of stars and planetary systems. This process of chemical recycling has progressively enriched the universe with increasingly complex elements. Every atom of carbon, calcium, or iron in our bodies is part of a cosmic history that began long before the birth of the solar system. Every new telescope built by humanity expands the boundary between the known and the unknown a little farther. Instruments from the past revealed that Earth did not occupy the center of the universe, discovered other galaxies, and demonstrated that space is expanding. Today's observatories can detect gravitational waves, analyze exoplanet atmospheres, and observe galaxies formed only a few 100 million years after the Big Bang. However, all these advances have also revealed that we still do not understand the nature of most of the cosmos. The exploration of the universe continues reminding us that every answer represents only the beginning of new questions, and that the true reach of human knowledge continues growing with every new look toward the stars.
If you enjoyed the video, don't forget to like it and share it with your friends. Subscribe so you don't miss more interesting content. Leave your comments and click on any of these videos. See you next time.